Last talk of the day for Shmoocon2024. Please give a wonderful welcome to Ryan and Ari, who will be speaking on AI-enhanced hacks, model in the middle. So please give a warm welcome to Ryan and Ari.
Thank you, guys. Can you hear us? A little closer? Is that better? It seemed like there were a lot less of you when I was filling out the CFP form.
We also can't see any of you though, so this is actually good.
Anyway, my name's Ryan. This is Ari. We're going to be talking to you about some work we did on using AI and hacks. So we will go ahead and get started. Oh, come on. There we go.
This is our little pay the bills statement, so you have to endure 2 of these. But we work at In-Q-Tel, which is the nonprofit strategic investor for the national security community. And we sit at the intersection of venture capital, government partners, commercial startups. And so this gives us a very unique lens into emerging technologies, promise, and areas for improvement. Next slide, please, Ryan. And so we specifically work at IQT Labs, which is part of what we call our capabilities business at IQT. And so we work on proxy problems of national security interest in the open source. And we primarily build proof of concepts and demonstrators, and you can find us on GitHub. And generally, we're looking to either de-risk emerging technology by better understanding its limitations, by hacking around with it. And sometimes we even find a partner to take the work that we create and scale it. And one last thing is that our opinions here are our opinions and not the opinions of In-Q-Tel.
At least in any legally meaningful sense.
Right.
In terms of who we are, my name's RyanAshley. I'm an engineer who kind of turned going rogue into a career choice. So,
Yep, I'm AriChadda. I'm a data scientist, and there's a lot of people bullish about AI right now, and I totally get that, right? I remember the sense of wonder I felt when I trained my first model, but Ryan and I spend most of our time on the flip side of that coin, looking to understand limitations of AI, adversarial use cases, et cetera.
And so in terms of what we actually want to show you today is based on some work we did, and we're going to demonstrate a way that we used an ML model as a component of an attack chain. And we want to show you not only that this is possible, but that this is relatively accessible. If there's one premise that's sort of fundamental to this presentation, it's that I'm a deeply unspecial person. I'm not a super genius hacker. I'm not a crazy smart data scientist like this guy. I just know how to read docs and put things together. And so this is within the scope of possibility for pretty much anybody. So first, a little bit about how we got here. I have the good fortune to work with some fantastically smart people who build some crazy, interesting toys. And then for reasons that I will never entirely understand, they hand them over to me and let me kick them around to see what happens. And so recently we were dealing with this system that had a bunch of different components, one of which was a security camera. That's going to become kind of important here in a moment. And sort of the way the project transpired, we were supposed to start it in January or something like that, and it kept getting delayed, and it kept getting delayed, and it kept getting delayed. And I had a lot of time to sit and think about it and sort of quietly seethe, but also sort of embroider what I plan to do. And it became this playground for a bunch of different ideas that I've had over the years. So first, I'm going to go into a little bit of background about the system that we were evaluating so you can understand sort of what the pieces were and how it fits together and how we get to this attack that we're going to be showcasing in a moment. So one of the problems with machine learning is that labeling is one of those things that's fantastically hard until it's easy. So up there in the top, you'll see 2 pictures. That's my cat, one of my cats, and my dog. And it's very easy to tell which is a cat and which is a dog. If you look at the picture below it, and I've got to give a huge shout out to Ari here because he noticed in the first slide. So one of those planes is a Boeing 737 and one is an A320. And how many of you think you could, with any sort of accuracy, tell the difference between those two? Show off. Also, huge thanks to Ari here because he noticed in my original version of this slide, I had used Airbus's demonstration A320, and it just said A320 in huge letters across the side of the plane. So I felt like a complete moron for missing that one. Actually, the original design came from one of the folks who spoke earlier. If you guys saw Luke Burnt's talk, the original idea was this system Skyscan. So all planes, well, all commercial aircraft, civilian aircraft, and a lot of military throw off this signal. It's an avoidance detection thing, right? It basically is a transponder on the plane that's constantly sending out a beacon going, I'm here, here's where I'm going, here's the speed I'm going, please don't run into me. And you can pick up on that transponder. It's an avoidance detection signal, so it's meant to be sort of easy to pick up and read. In fact, if any of you have ever used like FlightAware or anything like that, that's how they're getting that information. They pick up those signals from the transponder. You can do an FAA lookup in their database. It's a big CSV file. Don't get me started. Anyway, so the idea behind Skyscan was what you could do is pick up that signal, use the location information encoded in it to point a camera at the plane, take a picture of it, tag that picture with all the metadata from an FAA lookup, and then use this system to train a machine learning model to look at aircraft and determine what kind they were. Very, very clever. So like I said, we originally did this on this system. There's a picture of one of the demonstrator units over there. The demo today does not involve that for a number of reasons. One, it's really heavy. It's really heavy, and I didn't want to carry it around all day. Also, that camera, it's just like a security camera that's been flipped upside down, but it's still like $1,500, and I don't want yelled at when I drop it and break it. They don't expect me to be responsible with corporate assets because I've never given them any reason to think that I would be. And also, like, all the information about the original stuff is in a publicly available report that you could go look up should you so desire. So sort of the rationale behind why I did this way, right? Because I could have sort of demonstrated the risk inherent to that system in a bunch of different ways. Didn't have to do it this way. But I work with a colleague, a gentleman named Bob Glykoff, fantastically smart guy. And he and I have been having conversations for years, and he tells me that someday cyber's going to be totally the domain of AI and ML models, and humans aren't really going to be involved at all. I mean, I don't want to bet against him being right. He's a really smart guy, and he's been at this a long time. But it always kind of nagged at me that he was skipping some important steps in there. Like, it's very easy to say that, but there's a lot of legwork to get from where we're at now to that point, and what does that look like? And so I kind of set out to test his assertion by deliberately picking a relatively simple, relatively well-understood ML task, right? Image recognition, there's a lot of literature about that, you can go read that, and a very simple sort of technical attack chain, right? A man-in-the-middle attack. Again, this is a very basic sort of thing, easy to understand, easy to learn, well-worn. So if you can't get these two things to work together, that sort of blows his entire thesis out of the water. And if you can, that sort of enables you to start thinking more about like how to build more sophisticated tooling, how to build more complicated attack chains down the road. So I freely concede this is a starting point. Also, quite frankly, like, do you guys know who George Mallory is? They asked him why he wanted to climb Everest, because it's there. Like, I saw that I could do it, and it seemed cool as hell, and so why not, right? What you actually need to sort of get started doing this, very, very straightforward set of preconditions. You've got to be on the same L2 subdomain, L2 broadcast domain, sorry, which is a really fancy way of saying that you have to be able to get an ARP packet between the two endpoints you're interested in. So there can be switches between you, but not routers. And you need to know like what the data going back and forth between those two things looks like. We've used images in this case, but it's not restricted to that. You could work on any type of data that you can train a model to operate against. So text is on the table. I have some friends who are working on trying to do interesting stuff with training models against like RF data. So that's conceivably an option. You know, the sky's the limit. So for the purposes of our demo, this is kind of the basic architecture. An IP camera Essentially, the way those work is you do an HTTP GET request, and it hands you back a frame of video. This is how, either the HTTP or RSTP, RTSP, I can't remember which one it is for the camera protocol, but one of the two. This is the basic paradigm. And so we've essentially mocked that up in our demo purposes with an HTTP server that returns an image. And so what happens within the attack chain is we create this scenario where we reroute just one particular route that we're interested in. And that's important because when I was originally doing this, again, there was a camera, it had like a PTZ system. You could repoint this thing. So any of the PTZ commands were still going through this top route, right? But if you were asking for an image, you were going through infrastructure I controlled. So everything looked normal from the operator standpoint. It was only on the output side that you would be able to notice any kind of difference. And now Ari is going to talk a little bit about some of the model pieces of it.
Yeah, and so that interceptor block that Ryan showed you in the last diagram is basically just a model inference API with some housing, right? It's a pretty standard pattern that you're going to see over and over again. When you're selecting a model, though, there's really a two-part question you have to ask, and this is pretty intuitive, but I'm just going to spell it out. It's what data am I working with, and how niche is the thing that I'm trying to accomplish? If you're working on kind of a well-trodden path, right, like in our case, image data, right, well-trodden path, there's a lot of pre-trained models that are available that'll suit your attack very well, especially because we're doing things that are sort of not very nuanced, right, in kind of the first demo that we'll show you. And you can just pull those down, work with them very easily. If you're trying to do something more niche, right, especially if it's with a more abstruse data type, you're going to have to train your own model, right? Ryan talked about RF data, audio data, like you're going to need some pretty deep expertise in those domains. I burned 9 months of my life trying to do work with underwater audio. It's a bear, right? You'll get the best results, though, if you can capture data from the system you're trying to attack in the recon phase. And the more of that you have and that you can work with, the better your system is going to perform in your actual attack. General idea of you have things that are in distribution versus out distribution. Your models are essentially just fitting distributions. The more of it that you can do that's relevant to your attack, the better it's going to work. And generally what you find is there's this kind of trade-off between accessibility of a problem, the flexibility of your system, and the nuance that you're trying to accomplish when it comes to a model-enabled attack. And we'll discuss this in more detail after we show you a few demo examples. Next slide. And so we have kind of two variations of a demo to show you. One is with the pre-trained model. One is with one we trained ourselves. This first example is with that pre-trained model. And don't try to parse the diagram on the slide. Just note that it's complicated. This is one of those like eye candy things, right? Someone has done all the hard work for you. You can just pull this thing down and use it like an API, right? And so our first example is going to do kind of a pixel swap on an image that's like one subset of 10 animal classes, right? And this architecture in particular is trained on a very large data set of objects released by Microsoft called the Microsoft Common Objects in Context data set. So this gives you what you could call like fairly generalized performance. If you're working with one of those 80 classes, you can just pull this thing down and go from there. And that size of the data set is what kind of gives you that some level of generalizability. And then the specific weights we used, in this case, were the smallest variant of the architecture. And the general idea is that if you're just waiting for an image to come across, you sort of want to make your inference as quick as possible to sort of make it seem imperceptible to the user, right? And you're kind of mapping your attack speed to what you're trying to do. And so we ended up using the smallest architecture here, but feasibly, depending on what you're doing, there's kind of a nexus of trade-offs there as well. And Ryan, fair to say that you're a software engineer, right? He pretty much strung this first demo together all by himself, right? Which I think tells you how accessible this stuff is. And if you just treat a model like an API, you can pretty much get off to the races pretty quickly. Next slide, please.
Yeah. And sort of one thing that I just want to add to what he was saying about like the inference speed thing. I've talked to several other data scientists, and it was surprisingly difficult sometimes to explain to them that I cared way more about inference speed than I did about like accuracy or F1 score. Just a interesting difference in mindset.
Yeah, and one thing that I should have mentioned is we didn't want to bring in extra hardware along. So all of this stuff is running on like a Dockerized CPU on our Macs here, right? So that was kind of an additional consideration of like when we're picking a model, we needed to be able to do CPU inference very quickly, right? So no acceleration there.
And that was driven a lot by the original use case, right? Because that Skyscan unit was literally meant to be taken out into like a field by an airport somewhere, and you just set it there, like it can run off of battery power. It's meant to be run unattended. So we needed to be able to run on infrastructure that could be taken to the target.
Yeah, and so our second example, we trained our own model. And it's really just to display a few kind of parameters, right? To that accuracy sort of speed trade-off that Ryan was talking about. And so one thing you'll note, right, this model is a heck of a lot complex than the last one we showed you, and it's like almost a decade old, right? And we didn't pick the most performant model in this task. We're not looking at any of those sort of vectors. It's really just to show you that you don't really need bespoke hardware or other resources to accomplish an attack like this. You can train this model exclusively on a CPU in like a pretty reasonable amount of time. And in kind of the second demo we'll show you, we're doing 9 inferences in series, and you barely even notice, right? It's pretty imperceptible. Which should make this attack reasonably difficult to detect. And because we didn't try to create the most performant model, you're going to see errors. And that'll be a really interesting thing, because you're not going to get an 100% success rate on this attack. And that might be a good thing, right? Because it makes it more difficult for that attack to be detected. And so we'll give you more on that after the demo as well.
So just really quickly, in terms of mechanically the way this works, the attack infrastructure is split into 2 pieces. There's one container that I call the attacker container, and it essentially is running an Nginx reverse proxy that basically looks at the requests coming through it and then decides based on that route, right? You can see up top there, if they're looking on that image route, then I forward them along to my interceptor, and if they're not, I forward them along to their original target and just transparently proxy them in between. That way I'm only acting on and only interacting with things I'm actually interested in, care about. This is just sort of a brief note of a thing that I found interesting when I was trying to convert this from something that used physical hardware to a Dockerized demo. So originally I used a UFW rule because so if you've got a service, it's not going to respond on an IP address it can't bind to, and it can't bind to an IP address that it doesn't think is associated with a particular NIC card. And so what you have to do is you have to have some kind of construct that will do a masquerade operation to say, oh, pretend anything coming from this IP is actually going to this IP that you actually own, which is basically fancy NAT. And so physically I used UFW to do that. But you can't do that in a Docker network because both Docker and UFW under the hood are manipulating IP tables rules. And I actually read something really interesting recently. So just as sort of a caveat to you guys, if you're using UFW and Docker in production environments in particular, there are some weird edge cases where they'll start stomping each other's IP tables rules, and you'll end up with, physical ports exposed. Well, not physical ports, but host ports exposed that you didn't necessarily think were exposed. So just be aware of and keep an eye out for that. And so with that said, we're gonna launch into our demo really quick. All right. So get a couple of pieces up here. All right, so you guys can see, this again is my mock-up of an IP camera. It's just pulling random images from, oh, please don't do this to me now. There we go. All right, so it's pulling random images from, what is it, the VO, it's
Pascal VOC, the Pascal VOC data set, just think of it as a collection of a bunch of images that are outside of the distribution of this model's been trained on.
So I'm just going to flick through a bunch of pictures, and I just want you guys to pay attention to, like, particularly the different animals that you'll see. There's some birds. Oh, baby. All right, so this is just normal expected system behavior, just showing you sort of what's going on and how it works. And now I'm going to go ahead and start my attack here. And just bear with me for a moment. It takes a second for everything to start up. Do 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 do. Little hold music. Oh no. That. Okay. Got it. All right. We're going to switch, and Ari's going to do his bit, and then we'll come back to mine.
Perfect. Live demos, right? Hopefully this one works. Perfect. So pretty standard screen here, login screen, right? We're going to be looking at the CAPTCHA specifically for this. And so generally you have 9 images, right? Those are the 9 images we're going to do inference on. We're specifically interested in the cars. The way we have this set up, there will always be 4 cars in this. And the login button just refreshes the whole thing. So as you can see, more random images. Should be 4 cars, 3 planes, and 2 ships. And now we will start the attack. Takes a second to do its health check. Waiting for this to say healthy, and then we can move on.
That was the original goal, yes. Oh, sorry. The question was what the original goal of these attacks were. And so, as I said, the system that we were originally evaluating was designed to gather and label a data set of aircraft imagery to train a model on. And we were trying to show that you could essentially poison the data going into the training of that model.
Right, but like in most cases, right, you're pulling, sorry.
So the question is, how likely are you to be able to practically exploit that as a vector without knowing or understanding what the training data and the training pipeline is for a given company? Would you say that's a fair? Or having access. That's a fair question, and it's hard to say without knowing. Like, I don't work for OpenAI or Microsoft or anything like that. I can't really see into it. And I think it's worth noting that I sort of want to also disambiguate the technique that we're trying to show here from that original use case, right? So that's what we were trying to do with it, but you could use the same thing, the same tooling, the same technique to accomplish other ends.
Generally, though, I will say that the majority of data science applications are starting from I pulled down X data set from some, web server endpoint, whatever, right? So in OpenAI's case, they're doing their own scraping, right? We just had a great scraping talk not too long ago, but
I'm just while he's talking, I got everything running, so.
perfect.
All right, so. Yeah. Baby couch. Okay, so there you go. You see that part of the image has sort of been replaced there. Unless those people have a weird rug. I don't know. But no, actually, I can go over here and look and see that it thinks with 54%-ish confidence that there was a dog in that image. Nothing there. There's one. I want to see if I can get kind of a good one with. See, there's a case where it misses it, right? It doesn't work foolproof all the time. So part of that is the way I've designed it. You can see here that I am essentially looking for different levels of confidence depending on what type of animal it is. These are totally random numbers. I have no, like I just picked them, copy pasted most of them. But you can exercise a lot more control and sophistication and nuance over how you decide to impact something. The other thing, let's see if we can get birds. I'm looking for much higher confidence.
What's interesting about that too, right, is if my confidence threshold is high, I will have relatively few detections, but like they're probably pretty likely to be that thing. But in my overall data set of cats, right, like maybe I'm poisoning 20% of them, that's sort of interesting, right, because it hides you in that distribution a little better. And so we're kind of trying to think of confidence even as like an attack parameter that can be tuned in these attacks.
There we go. There's a good example. The model that we're using actually can identify multiple items of different classes within the same image and give you a bounding box. So that's just to give you an idea of sort of, if you wanted to, the level of control you could exert over what's coming through as well, right? You can see I'm finding, looks like 4 different, what it thinks they are. 4 different cows in a field there, and it's replacing all of them. So, and then now we'll switch over to Ari and.
Perfect. And so, quick example here, we're replacing the cars that were detected with this click me sign, and so you've kind of like invalidated the CAPTCHA a little bit, or the utility of it. But let's see if we can get some errors. This looks like another good one. Just for like demo purposes, essentially. Right, and one of them, so this car was kind of missed, right? And that sort of leads back to the idea of like confidence is something that can be tuned. Error rates are also something that can be tuned, right? So my sort of the perceptibility of this attack decreases a little bit when I get things wrong occasionally, right? And so in this case, this is one where we had a false negative, right? We missed a car. Occasionally, too, you'll get some like false positives. This is another good one.
Good.
You could do that, right? Like, we're just trying to demo like a hypothetical.
Yeah.
So
The question is if the intent was to bypass a CAPTCHA in some form, and the answer to that is sort of not necessarily. Again, we're showcasing that if you have an image coming across an HTTP and you can intercept it in this way, you can change it. So you could conceivably use it that way, but again, we're trying to like showcase different possibilities of this technique rather than specific use cases.
Yeah.
Ready to move on to? Yes. All right. So, slide. All right.
And so, like, just like any engineering problem, right? And you have some trade-off structure whenever you try to do something. when working with a model, there's kind of an additional 3 ones that I'd say you have to consider. So if task performance, this is like your ability to do the thing that your model is doing, is really important to you, you're probably going to have a more sophisticated architecture. You're going to require more data about the phenomena of interest, negative examples, things like that. You might have to do more recon of your system that you're attacking. This could be difficult or easy to attain. Like it really depends, right? A more sophisticated architecture, though, typically has a slower inference speed, meaning that if the system that you're attacking is fast in relation, your attack will be pretty perceptible. Though if you increase the sophistication of your hardware, which comes with both monetary and developer time costs, like in our case, going from a CPU to some sort of acceleration hardware, right, like a GPU or an FPGA or even an ASIC of some sort, you can sort of bring that inference speed down significantly at some cost, right? And so as you're thinking through designing an attack that incorporates a model, you're also starting to think through this nexus of how do I work with these 3 trade-offs, which are trade-offs that every data science application that uses a machine learning model thinks through. And so sort of, foot stomping this idea of side effects and error rates being sort of a parameter that you can tune is we wanted to show you kind of a model that performed really well at its task and a model that performed not as well as its task, right? But, and I think that unlocks something really interesting when it comes to designing an attack that's difficult to detect, right? You could feasibly train a model that does its job very poorly, but it does enough of what you need it to do to complete your attack, right? And so there's also somewhat of an unpredictable nature to failure rate, right? Once something's productionized, it's hard for you to control exactly what's coming through that pipe, right? That's why the whole industry of model monitoring exists for production models, right? Is I'm checking to see if the things that I'm getting are outside the distribution of what I've been trained on, right? When you're using an attack, you can't really control that. You could monitor it, right? And so you might have to rerun your attack multiple times. That's kind of something we're all used to. If you occasionally have things, oh, this works 1 out of every 5 times, fine, right? That might be useful to you. But the thing is, right, when out of distribution tail events happen during a real attack, it's not your Tesla autopilot having an accident, hitting a pedestrian, whatever it is. It's really a powerful obfuscation mechanism that you can use.
So, I just wanted to go back to when I started thinking about this, it kind of seemed complicated and overwhelming, and at the end of the day, it really boiled down to being able to use Python, a little bit of networking, and being able to basically read the docs on Torch Hub or Hugging Face or what have you to be able to figure out how to pull down the right model and interact with it in the appropriate way. And again, I just want to stress that even just the basic tooling that we've shown you, that I'm going to open source here after we finish this, it would work against any HTTP server returning images, right? We kind of showed off a couple of examples of that, but I'm sure you guys can think of a million more off the tops of your heads. So it's not just limited to sort of the use cases that we were targeting to begin with.
And generally speaking, we're thinking through it as this is a pattern that you could use, right? It's kind of a classic attack pattern that's enhanced or augmented or whatever you want to say with AI, right? It's sort of a question of what other classic attack patterns can be similarly enhanced, or take the same pattern, use some different modalities, and sort of do the same thing slightly differently, right?
And then in terms of just mitigation, because when I sort of previewed this to some friends of ours, this was the first question they asked me. These are essentially the same defenses that would use against standard attacks on ARP caches and ARP poisoning, but it bears repeating, segment your network, encrypt what you can. ARP monitoring is useful. I use ARP Watch at home, which is why I've called it out here, but there are a couple other tools in that space, whichever one works for you, whichever one you like. And again, just I want to stress sort of the ability we had here to scale, but also be subtle and precise. In a classic person in the middle type of attack, somebody has to sit there and monitor, or you've got some kind of script that's sort of a blunt instrument here we can be a little more precise with the determinations we're making and the modifications that we want to make based on those. And also just be aware that this is something that is out there and doable. It can be done if you want to. It can happen if you're in charge of defending things. And then just in terms of some other things that we would like to continue to investigation that we're thinking about going forward, I've been thinking a lot about like what something like this means for less detection for this particular case, but response, right? If you know that somebody has been poisoning a cache of images in this way, how would you go about detecting? Like I was, pretty brutal with what I was doing. It was very straightforward to see that. But if I had, put some sort of like non-visible mask across those images or just altered one pixel, there are much more subtle things that could have been done to manipulate those images that would have been very hard to notice. And how would you go about seeing something like that and responding to that kind of incident? And then, other ways to sort of integrate these models into offensive techniques and tactics. And then I just wanted to take a moment to thank our colleagues at the labs, Nikhil, who was our summer intern who set up the test model we use, my friends down at Fredericksburg Hackers who've been super helpful and supportive, my wife and my kids for putting up with my shenanigans, and the organizers, volunteers, and all of you guys.
Thanks. Thank you for listening.
Yeah. And then, if anybody has further questions. So just to repeat the question, he was asking what was preventing the confidence levels from leaking out?
Meaning like if someone could see what confidence we were using to then like say this is above the threshold, you'd also have to have the model in order to like make that determination of like what's actually happening, right? Because that's only half the puzzle of saying like, okay, my prediction is over X, Y, and Z confidence. But without having that model, I don't have confidences to compare it against, right? So I don't know for a specific inference request, will it actually exceed whatever thresholds are in place?
I mean, whoa, that got a little loud. In theory, if you suspected something like that was happening, right, you could start fuzzing at that system and start saying like, oh, I'll start throwing data against it and see, whether what comes back is manipulated or not. So I suppose in that sense, you could start trying to gather some of that information about the ongoing attack, but I don't know. That would be a really fun question to investigate. My instinct is that it would be very hard to turn that into a viable determination without like a lot of data that you could put through it.
Yeah, I generally agree with that. I think fuzzing or like fuzz testing this system essentially is kind of what you're describing, right? I think it'd take honestly, it'd be a cool experiment to try, like Ryan said, but I'm not totally sure of like how much data it would take, right, to like accomplish something useful. That I think is like it's probably very like case specific.
Okay. So, but stop me for a minute. There's nothing that would stop you from building up basically a very similar sort of rig to what we did, but slotting in different models that you pulled from something like Hugging Face or Torch Hub and start seeing like, is this behaving similarly to these things I could pull down? That, in theory, then you could start dragging some interesting information out of it.
Yeah.
But again, that's going to require like a lot of volume and a lot of time and a lot of hardware, because just like spitballing off the top of my head, trying to think about the system you're you're talking about, that turns into a Kubernetes cluster just like that. Nobody knows how those work.
Yes.
Alice. So the question is, are there potential defensive use cases for this technique as well? I think yes, but I haven't spent a huge amount of time thinking about that in detail, right? You could, as you say, do some things with sort of privacy types of constructs. I could see doing some interesting things in like honeypotting types of things with it in a similar vein. So the answer is yes, I think that those use cases are there, but I can't just like rattle them all off.
So the question is, I'm summarizing, you can jump in if I'm wrong, but how would you tell if an image has been edited, right? Are there sort of capabilities you can use for that, right? That's kind of the whole field of like deepfake detection, right? Of like, can I tell if someone has done something to my image? And people have done some work to varying levels of success of like detecting certain kinds of aberrations, right? But it's very dependent on like the sophistication of that aberration and like generally how many pixels it takes up in your image, right? There was like early on, there was a lot of interesting work like looking specifically at eyes, right? Because deepfakes were really bad at making good eyes in videos. And so like that was one people zeroed in on very quickly. I know Facebook ran this like deepfake detection challenge for a little while looking at like face swap detections. I'm not totally sure like how far the field has come, but I do know that it's lagging to what we can do from like an produce deepfakes capability.
So on the image front, I don't know of any particular tools that are dedicated to finding manipulated images. The caveat to that is I am in no way, shape, or form a forensics expert. So, you know, there are, I'm sure, people wandering around here who are much more knowledgeable than that, and I don't want them yelling at me later. File creation, I don't think that's going to be super viable because the way we did this, everything's operating in memory. I'm not using any temp files. This is all happening in byte strings back and forth. So that's out. In theory, if you had some fairly sophisticated monitoring, sort of maybe on your switches or your SIM, like you could see just differences in the byte string basically at the source and at the destination, right? But that's just going to tell you that it's changed in transit, not what changed it or why. So yes, because what I actually did on the original version when I was dealing with the unit, it slowed it down by about, it was usually between 400 and 500 milliseconds. And so what I actually did was on that Nginx reverse proxy, I just had it add like a half millisecond delay to everything so it looked the same across the board, because I sort of professionally cheated things. It looks like we are being told to wrap it up here. We've got 5 minutes left. Any more questions? Sir.
So yeah, the question was, in the example with the Airbus A320 and the Boeing 737, the Airbus plane had its landing gear deployed, the Boeing did not, right? If you had a data set that kind of over-indexed on those two features, right? So you had all your Airbus aircraft had all landing gear, and none of your 737, or very few, had those landing gear deployed, right? Could your model over-index on that fact? Absolutely, right? There was some like research done quite some time ago now of the example between this is like canonical at this point, but like your fox and your dog, and all it was looking at was the snow around the fox wolf, not fox, snow around the wolf, and saying this is a wolf, right? Absolutely, that these models generally pick up on like high value correlational artifacts wherever they are, right? That sort of makes your process of data set curation so important, right? And this point of like having enough data too, right? Where if you collected a lot of images of Airbus A320 planes, for example, right, feasibly a large percentage of them shouldn't have their landing gear deployed, right?
But it's also worth noting that in actual usage, this is going to be capturing images of planes from 30,000, 40,000, 50,000 feet away. One, they're going to be high up enough that they're rarely, if ever, going to have landing gear deployed. But two, I was also trying to make sort of a criticism, like the team that built Skyscan, and I'm not throwing shade here, this was just sort of an intellectual argument that we were having. They were kind of tacitly making the statement that by using this autonomous labeling construct, you could essentially turn unsupervised learning into supervised learning, right? And the assertion I was making is that no, there are no free lunches. You haven't turned it into unsupervised learning. You have changed the point at which you have to supervise the thing, right? Because now instead of supervising the labeling process, you have to supervise the system doing the labeling process, right? And once you've made it an autonomous system, a rules-based system, it's subject to being gamed just like any other rules-based system. Does that sort of answer your question?
One last point I want to make, Ryan. The other piece of that too is, right, is like when you're cross-correlating two data sources, right? So in the plane case, it's ADSB in the image of the plane, right? We did some work on AIS and like hydrophone acoustic signatures of boats, right? ADSB, pretty well regulated, like most of those messages are what they are. AIS is not like that. It is a mess. So you are it's like lowest common denominator when it comes to like data quality of like, if whichever one of those is worse, it's going to pollute the heck out of your data set and make it very difficult to train models.
All right. Well, thank you guys.
Thanks.
And ladies, don't mean to be